Okay, so he's done simulations of an Ising model. L must be the linear size, so it's in 2D, okay? Seems pretty big. Oh, it's, I don't know. So they're different length scales, so. These are right at criticality. So each one of those pixels is pretty much resolved by the projector, but it's a spin up and spin down. So you use 4 different images, and they're at different length scales. And no, I'm just looking at them. So different images come from different, there's one big image, and then the next one is part of the other one. So let's see how they all fit together. So the question is, can you tell which is big and which is small? Yeah, so that one's a smaller piece of the bigger one and so on. Isn't that crazy? So when you go back here. So the point is, this is what scale invariance looks like. If you just looked at any one of these, by themselves, you can't tell what length scale you're at, right? But once he tells you, there's a drastic difference in length scale between all of these things. Yeah, so that's the first one. Look how small it is in this bigger picture. That's right at criticality. It's got me in another movie. Okay, so we're going to talk about this today, but these are 3 configurations close to a critical point. And B is the size of a block. Okay, I'm going to explain what block spins are. So he's doing the same thing as he just sort of did. He's just zooming out. Okay, so he's changing the scale. And I'll talk about what the renormalized temperature is, so don't worry about it too much right now. But okay, so here you have 3 configurations. It's the same. It looks very similar. But the difference with the last video is that this one is not quite at TC. It's slightly below TC. So TC is the Jahn-Sauger temperature, 2.269. This one's directly at TC. And this one's just very slightly above it. But these are all finite size systems. And, in principle, that little epsilon distance away, shouldn't really matter in some sense, right? Or does it? So what he's doing is it's like the last video, except he's just zooming out here. And I'll explain this axis in a minute. But so here on the left, he's just zooming out, and there's that little piece. But as you zoom out farther and farther, he's done massive simulations to get these snapshots. You basically see what happens is you get all white, and it could have been all black. So basically, you're seeing the spontaneous symmetry breaking. And it's evident at some length scale. So B went from 1 to 170, or something like that. So that's kind of like the length scale that he's, so 2, 4. Keep in mind what that B is, and I'll define it later in class. But what he's doing is he's just successfully changing length scale, so he's zoomed out on the image. And it's equivalent to, the low temperature state once you're at a very sort of coarse grain length scale. So next is the high temperature one. It's only 0.003 above the transition temperature. But as you zoom out farther and farther, it looks totally random. And that's basically like, each one of these little blocks, which is some coarse grain spin, which I'll define, is essentially randomly up or down at that length scale. So it takes a very large length scale to see it, but it's definitely a different state than this state. Even though it's barely separated from it in terms of actual temperatures. And what happened on the axis here was something we'll define today. This is your RG flow. So he's done a renormalization group, essentially treatment of the temperature. And he's showing how that this temperature, very close to the critical temperature, but below it, is equivalent to the 0 temperature case. And in this case, you're slightly above. It's equivalent at some very large length scale to the infinite temperature case. So this is precisely at the critical point. So it just doesn't matter how far you zoom out there. I want the critical one again. Oh no. Oh, wrong one. So the critical one looks the same at all length scales. And that's because the correlation length is infinite. So there is no length scale. Here there's a length scale. The correlation length is very large, but once you get to this scale, you see what the correlation length is. The correlation length is like this, you know, and as you scale out, you finally see, and same here, here's a correlation length, maybe it's like this, you know, whatever the size of these characteristic clusters are. But at some length scale, you lose all notion of that correlation because you've made the system bigger than the correlation length. So here you might think the correlation length is like this big, but when you scale out, you start seeing, oh, there's another length scale, well, there's another length scale. And it turns out, well, there can't just be all these different length scales. So there really is no characteristic length in that case. So the essence of the renormalization group, which we're going to start deriving today, is this procedure. This kind of encompasses the idea that you're zooming out to different length scales. For those of you that missed it, let me play the first one. So if you're sitting right at the critical point, and you look at these different length scales, you can challenge yourself to ask, you know, which length scale is which. So they're vastly different. But you see that, you know, there's definitely small length scales and a very large length scale. That's it. That's all you get for movie day. Oh, wrong way. So today we're going to start talking about scale invariance and use it to derive the renormalization group. So scale invariance is exactly what you saw in those pictures that were precisely at the critical point. Just to put it all in perspective, remember we derived the correlation function. I can't remember if I use phi's or m's or sigmas or what, sigma I maybe. The two-point correlation function. It gives you the probability, you know, or it gives you the correlation length, which is the probability that two spins separated by some distance are correlated in some sense. So it's also a measure about how fluctuations, you know, destroy the correlations. Because really what it is it's the fluctuation from sort of the mean value, right? So these influences, or this, the influence of this, of one spin on another, occur over a characteristic distance. And as you know, it's defined by Gij going like, so you need a minus Ri minus Rj over Z, which is defining the this characteristic length or distance. Okay, so it's all stuff you've seen before. In some sense, it cuts off the correlation function. It's like you have an exponential envelope, and the correlations are cut off, when that envelope decays to 0. And this correlation length is what defines the size of that envelope. So it's like the cutoff. So when close to TC, as you know, the correlation length diverges. And what it does is it makes the microscopic length scales, or the short length scales, irrelevant. So as you saw in that picture at criticality, when you're zooming out, it doesn't really matter what the short length scales are doing in some sense. That's all the physics related to A, the lattice spacing. At some point there was some lattice unit, or some lattice constant in those videos, but I mean, once you zoom out far enough, who cares what's going on down at the lattice? So this is the correlation diverging is essentially solely responsible for the singular contributions to all the thermodynamic quantities. Okay, which is sort of what we saw. Note when you're exactly at criticality, that cutoff is gone, as you saw. There wasn't some length scale where if you zoomed out enough, you would finally see that those pictures started to change. They're always qualitatively looking the same. So if you're precisely at the critical point, this exponential form isn't valid anymore because that correlation length is infinity. There's microscopic length scales. There's the interaction range. But at criticality, those don't matter. They don't define the range of correlations, at least in that long wavelength limit where we defined this correlation length. So there is no length scale, as you saw. There's no one characteristic length scale in those systems. So the form of correlations, Gij, changes as it turns into a power of the separation. something like d minus 2 plus eta. And eta is something we haven't defined yet, but we're going to study it in detail. It's called the anomalous dimension. Oh, I don't know how to spell that.
Yeah.
Close enough. So it's just an exponent that has been 0 for us, essentially. We haven't even looked at this in any detail. You're going to look at this very, very carefully on your assignment. So in the previous theory, in the Landau theory, we had mean field plus fluctuations that we solved with Gaussian integration, so Gaussian fluctuations it's called sometimes. We were very careful to include all symmetries. Maybe global time reversal symmetry, then we had spontaneous symmetry breaking. We can construct those Landau theories based on symmetries. But scale invariance, the absence of this correlation length, gives you sort of an additional global symmetry which hasn't been accounted for. And is also essentially the reason that sort of Landau theory breaks down when we're at criticality. I'm going to call it dilation symmetry. It means we have invariance of the system under change of scale. Okay? It's the same as saying scale invariance. So when we constructed the Landau theory, we use local symmetries. They're local in the interaction, but we didn't include any sort of dilation symmetry. If we did, it would work. But essentially, it's impossible to add this directly to the Hamiltonian to make some effective Hamiltonian that has dilation symmetry, except in one special case in 2 dimensions, which is when this dilation symmetry implies conformal invariance. But that's a special case that we talk about in some other class called CFDs. Okay, so. Okay, so in the case when you have conformal invariance, then you can actually make a lot of progress. But for us, we're not going to deal with that. So we don't have a way of rewriting our Landau theory to include this global scale invariance, if you will. So instead of doing that, we're going to take a different approach and look at how this type of scale invariance, or this additional dilation symmetry, when you dilate this length scale in the system, affects the free energy. So we're going to directly look at the free energy and examine its scaling properties, okay, when we zoom out in length scale. So the process of zooming out is called coarse graining. So we're going to look at scale, coarse graining and scale transformations of essentially the free energy. As with everything in this class, it seems, to make things concrete, let's think of an Ising model. And let me specialize to the case where it's nearest neighbor. So the range of interactions is the same as the lattice constant A. I'll use J. Okay, I have a sum over, so I usually have an IJ here, and I've defined JIJ as being a matrix of interactions. But now it's a very sort of simplified case where my J's only interact nearest neighbors. So like, you know. So my sites I and J are always nearest neighbors, and the notation we use is these angle brackets. So that's what that means. So this Hamiltonian defines the length scale. There's n spins, so let me just put 1 to n here. And then we'll use sigma I, sigma j. For the purpose of the renormalization group, since we're looking at the partition function, you know, somehow e to the minus beta h, if normalized correctly, yeah, say it as e to the minus beta h, then this was just 1 over the temperature. We're going to absorb into the effective, into the coupling in front here, J. So this will make sense. Remember that I had that movie and I was very close to the critical point, but slightly below. And I was doing that, and then there was a block transformation, which I'm going to do. The effective temperature scaled to 0, and everything turned white. So just in terms of strategy, what I'm doing is absorbing this temperature into this parameter J. Then we're going to see how that J changes as we rescale the system, as we apply scale transformations. And I'll give you a sort of concept of an effective temperature. I'll define it as K. So that my Hamiltonian H tilde redefined appropriately. It's called the reduced Hamiltonian. Reduced, I don't know what it means. And we'll drop the tilde. So at some point you'll forget that you're working on the reduced Hamiltonian, but when you're wondering, like, where's my temperature? Okay, so spins are now, you know, interacting with length scale A, but let's assume that they're correlated with length scale Z, the correlation length, which let's take to be much bigger than A. Okay? Or at least bigger than A. So since we're correlated over large lengths, I can imagine spins on a length scale of some constant times A, right? So A is this length here. So let's call that constant B. So imagine whatever that is, you know, a unit or a block of scale BA acts as a single spin effectively because it's all one correlated unit. This is defining a block in the Kadanoff block sense. So it's a real space picture of the RG. Okay, so for example, I could have, I don't know. Imagine a 2D lattice. And I can define my B to be, I don't know, depends what the correlation length is, but imagine chopping this thing up somehow like this. So A, and then I would say B is equal to 3. So that BA is equal to this length here. And I would imagine defining somehow a spin for that block, which is like one step of this scale transformation. So just conceptually. So that, you know, I'm now dealing with some sort of spins I don't know what I'm drawing here, that live in the center of these blocks. Okay, so these would be called block spins. So the idea is to transform the Hamiltonian from a Hamiltonian that works on length scale A to a Hamiltonian that has interactions at length scale, you know, BA between some block spins. And I picked some convention or some choice of B, but there's no real reason why I did that. I could have also imagined, this one I'll use later, or maybe right now, so let me draw a property. So. Again, let me just draw a Hamiltonian of length A, microscopic length scale A, and I've just labeled the spins X's and O's. And imagine doing a block transformation where, so my new unit cell would be something like, I want to trace out O's, I think, or say X's. So like imagine what I'm left with are spins that are going to be interacting like this. That's my new lattice. That would correspond to a b of root 2, say. That's the length of the edge of this square. So there's different ways of doing this. That's the point. So conceptually, you're just imagining replacing the spins at length scale A with new definitions of spins. So in this case, you'd have to combine, say, these 2 degrees of freedom in some appropriate trace to make one block spin for this purple block, and then another block spin for this purple block. So you can imagine there's all sorts of different ways to do that. So the new degrees of freedom have to be obtained somehow from the old degrees of freedom. So for example, you could maybe average the spin states here. Maybe that makes sense here. You can imagine taking these 9 spins, finding the average magnetization, and replacing those 9 spins with, say, the average. Average, or maybe a majority rule, or you could just decimate. You can imagine just throwing away all the x's here, that would be decimation. So the point is, conceptually, kind of in real space, we have to define a transformation. We have to define a way of obtaining a new degree of freedom at a different length scale, BA instead of just A. Whatever B is, we have to choose that too. And then we trace out the spins that we're not using. Say, we trace these 9 spins out to give us a single purple spin. We trace out this pair in some sense to give us one block spin here. And then what we want to do is redefine the Hamiltonian that is the effective Hamiltonian, say, between these block spins here, or these block spins here. That's called coarse graining. And you can just picture it like that movie. You're zooming out at the critical point, and you have some pixels that you're looking at, and at some point, those pixels are being replaced by bigger objects, which have been coarse grained down so that the resolution you see is just some other pixel, right? So the idea is you want to start ignoring microscopic degrees of freedom that occur in that big purple pixel. And you have to ignore them in some specific way. So you're coarse graining, but those spins interact. And so you want to define an effective Hamiltonian between the block spins, between the purple spins. Hopefully that Hamiltonian looks the same. Hopefully its nearest neighbor at this new length scale BA. But that's not guaranteed. And actually that's the problem with doing this real space picture in dimensions higher than 1. say H goes to H prime, say, through coarse graining. If so, then we can, rescale the interactions. We can define that new Hamiltonian and then set BA equal to the new A, whatever, conceptually. And now what we've done is we've rescaled the problem so that we have a new effective Hamiltonian that's acting between block spins. It looks very similar, or hopefully it looks, exactly the same. The form is exactly the same. And then we can just essentially throw away that smaller length scale, keep the effective Hamiltonian, and normalize everything to unity again in terms of, or normalize everything to distance A. And that's called rescaling. Coarse graining and rescaling. What the RG is repeating this procedure over and over again. You have a new effective Hamiltonian in terms of the purple block spins. And then once you've normalized that, you do another scale transformation with another B that takes, say, 3 of these block spins and makes a block spin at the next sort of recursive level. And you keep doing this over and over again. And by doing that, you're tracing out, just like here you traced out all of these 9 spins, you trace out all the short range sort of fluctuations. And you're focusing on the long distance behavior. Okay? So if you're not quite at the critical point, as we saw in that movie, at some length scale, maybe your correlation length is very large but finite. If you keep doing this, you trace out the short range fluctuations, and at some point you see what's important. And what's important is the fact that you've missed a critical point. And if you're right at the critical point, then you'll keep tracing out short range fluctuations, or short range, I'm saying fluctuations because of the correlation function, but short range correlations. And you'll never find that length scale. You'll just keep going and going forever. So when you repeat this procedure, it gives you what's called the renormalization group. And what you're trying to do is study the renormalization group, study one step of coarse graining and rescaling to try to understand basically asymptotic behavior. So it's very different than analyzing the partition function through some effective action and taking approximations and doing perturbation theory. You basically want to see how the free energy is affected by this coarse graining and rescaling. And you're not going to do the full procedure. You don't have to do a calculation, to infinite sort of repetition. Like that's what happened numerically. You only have to analyze one step of the renormalization procedure. So you repeat this procedure. It's called the renormalization group. It should reveal the critical behavior, and the goal is to understand this with analysis of one step. So we're going to do a specific example in a minute on the 1D Ising model. And we're going to look at what that one RG step is, and we're going to analyze it to see what it tells us about, you know, the state of the system. Let me just go through the framework a little bit less generally, but not quite as specific as the example we're going to do. So when I say the jargon, you at least roughly know what I'm saying. So we have original Hamiltonian, H, and we have a partition function, Z. Okay, I've written it up there. And so let's perform one step of coarse graining. Let's use this lattice here. Imagine doing this lattice. And coarse graining out, which means, say, tracing over some spins. And let's just do one spin. So let's trace over those X spins. As opposed to O. Then the partition function, let me label the original partition function of n spins and the original Hamiltonian. We have some finite size system. Okay, so some redundant labeling maybe. So there's a trace over all spins, but I can artificially imagine sigma zeros and sigma x's. And after that operation, of tracing, I can just write this as the sum over sigma, what's left? O's. E to the minus, say, call it H prime. Which is just, you know, Z, there's a new number of spins, and there's a new set of interactions. So n is the original number of degrees of freedom. And n prime is the degrees of freedom after the trace. Okay. These original degrees of freedom interact with H. And the coarse-grained degrees of freedom interact with H prime. So let's, what is H prime? I've defined it through this equation here. So formally you can just say it's, you know, log of the trace of e to the H. And this is generally a complicated nonlinear relationship. It depends on that trace, right? So there's no reason why taking that trace is going to give you a nice, smooth relationship between H and H prime. And typically you can't calculate that in some meaningful way. So let's just ignore that precise detail until we do a specific example in 1D. We'll just call it transformation R. You could also label it with B, RB. The transformation depends on how you choose that scale, that rescale factor. It's not really an example, but I wrote it here. B is root 2. And you could have picked different conventions, essentially. They should all give you the same thing. But just from that partition function, Z, you could generally see how things scale, or rescale. So let's look at the length scale first. Any R, any distance between, say, I and J, will rescale such that, let's see, R prime is equal to B minus 1 R. That's what you're doing, essentially. You're just changing the definition of length when you do this rescaling. So most importantly, the correlation length is less than the correlation length at the smaller length scale. I mean, obviously, almost, but since that's true, what does it mean about our, position, I guess, in phase space with respect to criticality? Criticality means that this thing's infinity. So if this thing's very large and we do a rescaling, we'll see that it's smaller after the rescaling. So if it's not exactly infinite, then we're going to be driving the system away from criticality at this next length scale. So in that video, what was happening was when your TC is whatever, 0.9997, or T is 0.9997 TC, and you start doing rescaling, sort of this length scale started being driven away from, it gets shorter and shorter, it gets driven away from criticality. So it's like, depending on what side you're on, you're driving the system towards, essentially zero temperature or infinite temperature. If you're right at the critical temperature, that's infinity. So it doesn't really matter. So what you can imagine doing is also effectively changing the reduced temperature, right? Either making it warmer or cooler. And the reduced temperature, remember, has been absorbed into the coupling, K there. So we should expect that our effective reduced temperature is changed via this rescaling. The wave vector, okay, it's just like the inverse. The wave number Q prime will be BQ. This will be important later. Oh, Q prime. what we're going to do is eventually do this calculation in momentum space. Okay, so that'll matter later. But the number of degrees of freedom. Okay, so let's go. So the number of degrees of freedom changes. Should be less, right? You start out with n. Now you've rescaled n prime. D is a linear length scale, so it's v to the minus d n. Okay, so the total number of degrees of freedom is reduced. Reduced by the coarse graining. Makes sense? And this affects basically the rescaled free energy through the fact that the partition function, if we write it like this, is invariant. I mean, we're not throwing away at this point any degrees of freedom. We're just keeping the partition function invariant. If we throw away degrees of freedom, I mean, it makes sense to throw away short distance degrees of freedom at some point. That makes it so this coarse graining isn't reversible. You'll lose information, right? So if you just rewrite the theory in terms of m prime, you lose the information that corresponds to the Hamiltonian on the microscopic length scale. So from, let me just write it like that. It follows that, okay, so the free energy, the extensive free energy is equal, let me be careful and absorb beta into the free energy. So strictly speaking, it's anyway, so the free energy density, if that's what you want to call it, at the two different length scales has that relationship. That basically defines f prime. Okay, so the free energy density, where, you know, I've just called f beta f, scales like v to the d. So that's your first example of a scaling dimension for some physical quantity. We have a rescale factor. Again, we chose it somehow. That's the coarse graining, that defines the coarse graining, sorry. And the exponent of that is called the scaling dimension. So the scaling dimension is x. That becomes important very quickly in terms of what's relevant and what's irrelevant. So just as a note, at t equals tc exactly, as you saw in those videos, all that rescaling doesn't matter, right? The system looks invariant under the change of length scales. There's fluctuations of all length scales. There might be a microscopic length scale that has to do with the range of interactions. You know, and the longer that range of interactions, the bigger you have to zoom out to kind of get past it and see the scale invariance. So the system is eventually scale invariant. You know, at large enough length scales. Or so, let's just say essentially unchanged. So after successive RG steps of defining a new Hamiltonian, so by coarse graining, then normalizing stuff so that the Hamiltonian looks the same, and then doing a repeating. So after all these many RG steps, so you can write this as, there's a Hamiltonian, instead of prime, I'll use star. Eventually, if you apply this transformation, whatever it is, then the Hamiltonian's unchanged under that transformation, essentially. That defines H star as a fixed point Hamiltonian. And remember, this happened after many successive transformations. So let me call it limit of RB to the n. So recursively, you've done this from the original critical Hamiltonian. Okay, so H star is a fixed point. And these fixed point Hamiltonians is what controls all the long wavelength physics. So the idea behind the RG is you're searching for these cases where you start with a microscopic Hamiltonian, in this case a critical one. You perform the limit of all these transformations to find, at some point, successive RG transformations don't change. Don't change your Hamiltonian. Okay, I think it's hard to talk about generalities anymore. So let's do a specific RG transformation. We'll come back to these, especially this, and look to see what this, if you want, scaling theory implies for different cases. You can derive finite size scaling forms at critical points from this for use in simulations. So even this sort of general framework is very powerful. Let's do a specific implementation of the 1D Ising model. So my reduced Hamiltonian can be written like this: I plus 1. Partition function is basically that thing. Just a sum over all Ising spins. Remember what this thing means? Remember, the hardest part of this class is remembering what the trace means. We're going to calculate one explicitly here. So, okay, so I have a 1D Ising model. I have to do the equivalent of this procedure, some sort of coarse graining, and I'm in 1D. Let me label my sites. And let me define blocks. For which I'll make a new degree of freedom. And let's choose blocks of size 3. You could do 2. Maybe you will do 2 on an assignment. I don't know. I haven't written it yet. So this is your B. B equals 3. And you have to decide how to, I think I erased it. No, how to decimate or average or majority rule degrees of freedom. So that affects how you that affects like this procedure here for defining this Hamiltonian. So there's easier and harder ways. So let's decimate. It means you're basically just throwing away degrees of freedom. So let's call a block spin sigma I. I is just the number label. Prime is it means I'm at the next length scale, the coarse grained. And let's just define the block spin to be just sigma of, I don't know what to call it, the center. I've run out of imagination. M, middle. Okay, so I have a block spin here. Sigma 1 prime, that's just equal to sigma 2. Sigma 2 prime is the center, the middle. Here's the middle, here's the middle. Sigma 5. So I'm going to write my new Hamiltonian in terms of those degrees of freedom, tracing out the other spins. So how do we do this? Trace. Define a partition function. Okay, so let me write it like this. Sum over all spins. Okay, so I have that Hamiltonian. So e to the minus, well, it's e to the minus h, I have a minus sign out front. Convenient. So let me just write it. Let me write all the terms. That's easiest. One, two, 3, 4, 4. So by definition, these are all the nearest neighbor pairs. So the first position my block spin occurs, sigma 1 prime, is here. Okay, so I'm going to have to take the trace over this object. Let me look at these 3. And basically all I'm doing is the trace now, so. Sigma 1 prime is sigma 2. And sigma 5 is sigma 2 prime. So keep track of the block spins. This is a block spin, this is a block spin. I'm just decimating the rest. I'm just going to trace over them. So this is like the easiest thing you can do. I think I haven't shown you this in this class before. I got that like middle term, sigma 3, sigma 4. I'm going to be taking a trace over that. So when I take the trace, remember I'm summing over all terms and replacing sigma with their various values. So I have terms that are like sigma 3 is plus, sigma 4 is plus, and I have plus minus. You know, and I only have, these are Ising spins, so I only have 2 possibilities for this product, plus or minus, right? Since sigma 3, sigma 4, plus or minus 1, then this thing, right, if it's here, it doesn't matter. So it's just the hyperbolic, it's an even function. Oops, k. And this is an odd function, so if the product is minus 1, that minus sign just comes out in front. I can just write it like this. So it's just an identity because of the fact that you only have those 2 possibilities for that product. So I pull the hyperbolic cos out. Because I just want to write this thing in terms of hyperbolic tangent. Okay, and you can do that for all of those terms in Y. So I got 3 of them there. You're going to get 3 of these. I've just defined x to be that hyperbolic tangent. So don't forget, x is related to k. K is the reduced coupling. So it's 1 over T of J. So the temperature is inside of that K. So x is related to the temperature. Okay, so we have to take the trace over this thing. Okay, so this is the only crummy part. So let's just expand. Okay. I'll just do it. I'll just write the final answer down. Right. You can check that for fun tonight instead of going up. So when I take the trace, I'm keeping the block spins, sigma 1, sigma 2s, right? Primes. So everything with prime I'm keeping, and what the trace is summing over sigma 3 equals plus minus 1 and sigma 4 equals plus minus 1. So just note what I'm doing. So it's a sum, sigma 3 equals plus minus 1, and another sum, sigma 4 equals plus minus 1, and this is the original term, and all I've done is relabel 2 and 5. That's what the trace, that's the, if you will, partial trace over those degrees of freedom. Let me call that argument. Oh, I already called a y over there. So, okay. So I'm just summing over 3. So I'm just, instead of this whole trace, I'm just pulling out the traces for sigma 3 and sigma 4. So this trace is equal to, okay, I expanded just the square brackets, so don't forget your hyperbolic cos cubed. Oh. No. I'm pulling out that thing, so. And what term is going to survive from that expansion when I think about these two sums? I mean, every time a sigma 3 occurs in that expansion, that term is going to be plus and minus, right? And same with sigma 4. And even the product sigma 3, sigma 4 is going to have 2 cases where it's positive and 2 cases where it's minus, right? So the only way you can get a term that survives is if both of those terms are, both of those sigmas are squared. So it can only be that last term. So this is the block spins are left because I haven't traced over them. How many times does it occur? Some combinatorial factor. I mean, it's 1 in the square bracket, but you're summing over it. There's 2 here and 2 here, so there's 4, right? Okay, so that's it. That's the only hard part, is doing that trace. And it's easy for Ising spins in some sense, because the trace eliminates a bunch of terms by symmetry. Okay, so I got that thing, and I'm trying to write a Hamiltonian that looks like the original Hamiltonian. So it means that that thing here should somehow look like an exponentiated Hamiltonian with, instead of k as couplings, it's k primes, and the degrees of freedom are the ones that are left somehow. So let's just force it to look like that. So I'm defining k prime through this. Okay, so this is, by definition, tan h k prime. Okay, so I've I just expanded it in the same way I did over there with the original one. And so if I look at that, then my cos h, hyperbolic cosine of k prime, is just going to be related in some sense to, this equation up here. So then I can invert that to get just k prime. Okay, so the tangents in that equation, so it's got to be the inverse and x, right? So x is tan hk, right? So I can write it like that, which is just, I skipped a step where. Right, so that's this piece here and this piece here. Makes sense? So I forced, again, the sort of coupling to be nearest neighbor. K prime acts between sigma 1 prime and sigma 2 prime. And sigma 3, just to summarize, it's going to be 4 hyperbolic cos cubed which is just some constant times this piece, k prime, sigma 1 prime, sigma 2 prime. Okay, so now I have basically a recursion equation, because the Hamiltonian's forced to be in the same form with k prime instead of k. Okay, and the thing that I wanted right? So basically the trace, the partial trace of degrees of freedom over this object can be written like this with those definitions of, K prime. So the way that K prime scales is actually the important piece. It's like this is the important piece of the RG here. By analyzing that equation, you can determine essentially all the critical properties of your system. I mean, you could do it again. You could go to K double prime, but it's going to be exactly the same, right? Why would you keep doing it? The transformation itself is what gives you the physics. So just imagine doing it. Don't do it. Actually, but before that, let me just write the full thing. You have to do that for every, every 3 exponentials. So let me just write the final form. So do this part. Okay, so you had n spins total. Your b equals 3, so there's n basically over 3 remaining boundary spins. Which are the spins, 3 and 4. You have to do it again for 6 and 7, 9 and 10. That's what I mean, right? Well, you have that constant out front. You're going to get n over 3 of them. Then you're going to get a trace over the remaining block spins. Hamiltonian written in terms of block spins. And typically, you just don't care about this thing. Just absorb it into the definition of H if you want. So to be exact, we'll just absorb it into H. Now my partition function is exactly the same. Whether we normalize Hamiltonian. Okay, well, I still don't care what that thing is. Call it G. So for completeness, let me just write this. Cos H 3K. Some constant. Whatever. So that's just all the short, just a contribution of the energy from all the short wavelength degrees of freedom. So it's a little messy, but it's like the cleanest thing you can do. If you try doing this in 2D, so I'll explain some other day, it basically doesn't work. So H prime has the same form as H, with just a different renormalized coupling. Like I said, the main content of the RG transformation lies in this equation here. And so all that's left is to analyze that equation. How do I write it? K prime. Yeah. Or x prime, which is just hyperbolic tangent of k prime, equals what did I say? Tan h k prime equals x prime. Okay, so we'll analyze this next class. But the point is, again, that you imagine doing this again and again. So you have two steps. It's you start with x for your coupling, tan k. You rescale, you get this x cubed relationship. Then you renormalize, or you rescale so that that's your new scale. Then you do the procedure again. And as you do this, you're essentially changing the effective coupling, which means you're changing the effective temperature, right? So the way that this effective temperature changes defines how the physics of the system in the long wavelength limit looks. So when you scale to, when you do this recursive renormalization procedure out to infinity, those couplings will turn into either maybe high temperature, low temperature, or as we'll see, if you're right at the critical point, then they turn into the fixed point Hamiltonian, the thing I called H star. Okay, so that deserves some care in its analysis. So we'll start analyzing this specific equation on Wednesday. We'll see you guys then. Your assignments are due in 1 week, right? So on assignment 3, I'll give you maybe an example like this to work through. Maybe with a field, if you do it with a field, then you get like a more non-trivial RG sort of flow. I'll decide later. Questions? See you guys next week.